How are you? Right, today we are looking at the diagonalization of a matrix. Right, let us have some matrix given matrix A of order n by n and whose, I don't know if this is whose, but whose eigenvalues, values are lambda 1, lambda 2, lambda 3, and so on, and corresponding eigenvectors of matrix A, corresponding eigenvectors of matrix A are x1, x1, x2, x3, and so on. All right. Now I'm going to give you two known matrices. Now what do I mean by corresponding? It means that if I write them in pairs, I have eigenvector 1, eigenvalue 1 with a corresponding eigenvector, eigenvalue 2 corresponding eigenvector, and eigenvalue 3 corresponding eigenvalue, which means they are in pair because they have the same subscript that you can notice over there. Now, I'm just going to make a definition here, right? A matrix whose entries are eigenvector is called a modal modal matrix, which means M is the same thing as x1, x2, x3 until xn, you never know. And then you'll have a huge matrix because this thing simply states it's an eigenvector, right? In x1, there will be x11, x21, and so on until you have xn1, right? This column, it's for that eigenvector, right? The column 2, it's for this x2 that you'll see here. This x2, so I'm going to have x12, x22 until you get x and 2. This third column, it's for the third eigenvector, which is going to be x13, x23 until xn3, and then the last eigenvalue will be, your eigenvector will be x1n, x2n until you get xnn. Remember, because we didn't specify that you are dealing with a 2 by 2 or a 3 by 3, I simply said it's an n by n matrix. So we don't have we don't know, we have n columns and n rows. That's why you see that your last row has an n and your last column also has an n in it. So this is a modal matrix, is a matrix of eigenvectors, right? It's a matrix of eigenvectors, right? Our next one, it's called the spectral matrix. A definition again, a matrix whose entries, I don't know this word of entries, a matrix whose entries are eigenvalues, values in the main diagonal, is called a spectral matrix, which is denoted by S, right? This one is denoted by M, which is a model matrix, the spectral matrix. So a spectral matrix is something like this. S is equals to something like this. Remember, your eigenvalues are in the main diagonal. Another thing that you need to notice, the first column is for x1, so your first eigenvalue must correspond with x1. So I'm going to have lambda 1, 0, 0 until you have a 0, we have a 0, 2. Your second column must be here, it must be lambda 2, 0, 0, 0, lambda 3, until you have 0, 0, 0, lambda n. So lambda 1 is corresponding to the first eigenvector, lambda 2 is corresponding on the second eigenvector, your lambda 3 is corresponding to your third, and your lambda an, it's corresponding to xn. So if your first, if you say your first column, it's for the eigenvector 1 in a model matrix. In a spectral matrix, your first eigenvector must be an eigenvector, your eigenvalue that must correspond to an eigenvector in a model matrix. They must be in pair. So if you have an x1 here, you need to have lambda 1 there. If you have x2 here in the second column, again in the second column there you need to have x2 as an eigen value. Right, there is a theorem. The theorem states that, let me change color. It states that, no, I have blue already. It states that the inverse of the model matrix multiplied by the matrix original times M, I'm going to have the spectral matrix. Now remember, M and S are spectral matrices respective to A, which means the eigenvalues that you got from matrix A and the eigenvectors that you got from matrix A must be the modal and the spectral matrix. So you cannot take the modal matrix and a spectral matrix of a different matrix and multiply to a different matrix and think that this theorem will hold. Now the theorem will not hold at all. Now what you need to remember until we prove the theory, remember, let me just say note that A times x bar is equals to lambda times x bar. This was a theorem that we first looked that I first taught you that A times x bar is equals to lambda x bar, which means if you take a matrix and multiply it with an eigenvector, an eigenvector will be scaled with a particular factor of lambda. Right, the particular factor of lambda. You need to know that. Now let us first look at the theorem. Let's look at the proof. The proof is very important because it is part of your exam. If M and S are modal and spectral matrices respective of matrix A, then prove that M to the power minus 1 times A times M is equals to X. So you need to know how to prove this theorem. Right, you need to know how to prove the theorem. Now let us look at the proof. First, we will just assume, we'll just look at this part first. Looking at that part, so I'm going to have A times M. A times M, what does it mean? It means that A is a particular matrix, right? Times X, really. Because M, it's a vector. It's a vector, really. It's a vector, right? It's a vector. We're just going to assume this is true. We're just going to assume it. Therefore, we will say that AM is equals to A. Since M is a model matrix, is a matrix of eigenvectors, so we'll just say it's X bar. So we know that AM has the following entries: X1, X2, X3. So we have X1. So we have X1, comma, X2, comma, X3, comma, until you reach Xn, right? And then what I need to do there, take that A, multiply it inside. So we are going to have A times X1, comma, A times X2, comma, A times X3, comma, until you have A times Xn. Now, if you can see this part, note this part, you can clearly see that it's this part of the theorem, which means AX bar is equals to lambda AX bar. Because you are multiplying matrix A with an eigenvector, matrix A with an eigenvector, you should get below lambda times X bar. So, which is going to be lambda X1, comma, lambda 1, lambda 2, X2, lambda 3, X3, comma, until you have lambda n Xn. That it is your thing that you just proved here, right? It's something that you actually know that A times X, which is an eigenvector, is equals to lambda times X, which is an eigenvector. So this is a matrix. Lambda X bar and X bar, or X arrow, are eigenvectors, and lambda is just an eigenvalue. So when multiplying a matrix with an eigenvector, I'm going to get a lambda times an eigenvector. These two eigenvectors are actually the same thing. So that's why you see that X1 is the same thing, right? And also, if we prove M times S, right? M times S. Now let us prove A times S. So we are going to have, what is A? M, it's X1, comma, X2, comma, X3, comma, dot, 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 comma, Xn times S. What would you get here? What would you get if you think? You will get something like, because M times S must also give you the same thing. Which is lambda 1 X1, comma, lambda 2 X2, comma, because it's a model matrix times a spectral matrix. A model matrix is an eigenvector, and a spectral matrix is an eigenvalue. So do not get surprised when you say again lambda 3x3 for the second time until you get lambda nxn, like that. So we have proved two things here. We have proved that A times M is actually going to be equal to A times M is actually going to be equals to M times S. But if you look at the theorem has M to the power minus 1, which means there's an inverse over there. So how can you get an inverse to the other side? We're just going to multiply by the inverse of M on both sides. By doing that, I'm going to have M to the power minus 1 times A times M is equals to M to the power minus 1 times M times S, right? So by multiplying by the inverse of both sides, I'm going to have m to the power minus 1 times a times m is equals to. Now, what do you remember about this? Remember that when multiplying two matrices, a matrix and the inverse of that matrix, I'm going to get an identity matrix. So I'm going to have INS. And taking an identity matrix and multiplying to that matrix, you are actually multiplying that matrix by 1. Right? So that is the theorem. We have proved it. So in your 5 marks in an exam, so this is what we actually want. So whenever you are asked this question, this is what you must do. You must always remember this theorem. It's one of those things that helps. It helps, right? Let us look at a very simple proof on this theorem numerically. So given P, which is 2, 1, 2, 3, prove the above theorem. So we need to prove the above theorem using matrix. We can also do it using a 3 by 3 matrix. It does not matter really. It does not matter, right? It does not matter. But I'm just going to do a 2 by 2 matrix. So we need to get the model matrix. We need to get the spectral matrix. So this thing calls for the eigenvalues and the eigenvector. So please listen carefully. How do we find the eigenvalues and the eigenvector? We do not mind. So I do not mind explaining it all over again. So I'm going to have the determinant of P minus lambda I2 is equals to 0. Now, this is the formula that you need to write whenever you're trying to find the eigenvalues. It is called the characteristic equation. I don't know how I can write that. God. Yeah, me and English is something that will never mix. So it's oil and water. All right, it's a characteristic equation over there. We write I2 because the matrix that we are dealing with, it's actually a 2 by 2 matrix. If P was a 3 by 3 matrix, I'm going to multiply lambda with I3, right? And P is just the name of a matrix. The next thing that you need to do to find the eigenvalues, I'm going to write this formula. The determinant of, I'm going to subtract your lambda from the main diagonal. That is your main diagonal. That is your main diagonal. So I'm going to subtract lambdas on those entries. So I'm going to have 2 minus lambda, 1, 2, and 3 minus lambda is equals to 0. Right, you're always going to subtract lambda from the main diagonal and find the determinant of this matrix. So it's 2 minus lambda times 3 minus lambda minus 2 is equals to 0. Simplify this matrix. I am going to have lambda square minus 5 lambda plus 4 is equals to 0. Factorize. I am going to have lambda minus 4, lambda minus 1 is equals to 0. So lambda 1 is actually going to be 1, and lambda 2 is actually going to be 4. Remember that we are starting with the smallest lambda. That's why we're calling it lambda 1. The biggest lambda, it's lambda 2. Right. So if you have any question on this, you can leave your comment. Right, so we have lambda 1, lambda 2, and then we need to get the corresponding eigenvalue, the eigenvectors of lambda 1 and lambda 4. So this is what I'm going to do. I'm going to say 4 lambda 1 is equals to 1. For lambda 1 is equals to 1, I'm going to replace this thing. I'm going to replace this 1 to this equation there. So I'm going to have 2 minus 1, that is going to be 1, 1. And then I'm going to have 3 minus 1 is going to be 2 times x1, x2 is equals to 0, 0. Many students have asked me that, why do I multiply by this? Let us go back here. I love it when you guys ask these types of questions. Let us take this. Ax is equals to lambda x. Let me just take it. ax is equals to lambda x. Take the lambda on the other side. A minus lambda times x is equals to 0. You see, this thing mimics the same formula. It's a minus lambda times x. This is a minus lambda. This is x. That 0 there, it is that 0. So everything is done very precise here. Everything is done very precise. So do not get confused that why do I multiply by that? It is because of this formula, the characteristic equation. You see this characteristic equation here? It's the same thing as here. It's just that this one is pure. It's pure written. So then, how can I get the x1 and the x2 then? To get the x1 and the x2, we need to, the definition here, we need to find the Gaussian elimination of this part. We need to find the Gaussian elimination of that part. But because we notice that row 1 is actually going to be equals to row 2. Because row 1 is equals to row 2, and there is no row 2 without row 1, row 2 is actually going to be a 0 matrix when we perform the Gaussian elimination. It's going to be a 0 row. A 0 row. Because we have a 0 row, we are going to be left with the first row. And the first row has two unknowns, which is x1 and x2. Because we have two unknowns and one equation, the second unknown, we let it to be alpha, because it's the free variable that you are going to get. We are going to let it to be alpha, and then we need to use an equation there to write to get x1. So x1 plus 2 alpha is equals to 0. So x1 is actually negative 2 alpha. So v1 is actually going to be negative 2 alpha. And the rule in our university states that you need to take out the highest common factor of negative alpha. We cannot have an eigenvalue which is negative on top. So I'm going to have negative alpha. It's negative alpha. We are going to have 2 minus 1. So that is an eigenvector for lambda 1. Right. So let us get the eigenvector for lambda 2. For lambda 2, we have 4. The eigenvector for this lambda, I am going to have, I'm going to take this lambda here, which is 4, and replace it here. Now 2 minus 4, that is going to be negative 2, 1, 2. And then 3 minus 4, it's negative 1, times x1, x2 is equals to 0, 0, like that. Yes, let me just clean it. Times x1, x2, 0, 0, like that. Again, if you notice, row 1 and row 2, they are linearly dependent. Because to get row 2, you need to divide by negative 2 on the first row to get row 2. And you are going to have 0 row on the matrix. So we are going to say, let x2 to be beta this time. And then I'm going to have x1 minus beta is equals to 0. Use an equation that you prefer. You can use this one. You can use that one. It does not matter. And then x1 is going to be beta. So v2 is going to be beta. Take out the highest common factor of beta. Beta is 1, 1. Is 1, 1. Right. So now we need to write our m. We need to write our m first. What will be our m? Our model matrix. We are going to start with the first matrix, which is v1, which is going to be 2 minus 1, and the second one is 1, 1. That is our model matrix. And then we need to write our S, which is our spectral. Because your first row has a v1, your second row, your first row here must have lambda 1, which is going to be what? It's going to be 1, 0, 0. And your second row column has 1, 1. It must have your lambda 2, which is 4. Like that. So it must correspond. It must correspond. Right. Now we have found our lambda 1. We have found our m. We have found our s. And we have our a, which is p, really. Right. And the next thing that we need to do, we need to find the inverse of m. Now, to find the inverse of this, m to the power minus 1 is actually 1 over the determinant of m times m to the power c all to the power t. Now, this thing, m to the power c all to the power t, it's called the adjoint of m. It's always going to be written in this form. The adjoint of m to the power c all to the power m. Now to get the inverse, first we need to find the determinant of a. So let us do that. The determinant of m is going to be 2 times 1 minus 1 times negative 1. So it's going to be 2 plus 1, which is going to be 3. So that is the determinant of m. The next thing that you need to do, you need to find the cofactor of m, which is m to the power c. To find the cofactor of m, we need to use the place sign, plus, minus, minus, plus. We need to use them precisely. Right, what is the cofactor of 2? To get the cofactor of 2, close this row, close that column. We are going to be left with 1. So I'm going to take that 1 which is left. I'm going to multiply with the plus, which is going to be 1. What is the cofactor of this negative 1? To get the cofactor of that negative 1, we need to close this column, close that row. We have a 1. Take this 1, multiply it to that negative. So 1 times negative, 1, negative 1. 1 times negative, it's negative. Now we need to find the cofactor of this one. Cover that, it's going to be 2. What is the cofactor of 1? That is negative 1 times negative, that is 1. That is a cofactor matrix. And then we need to find m to the power c all to the power t, which is the adjoint. So we need to transpose this. To take a transpose of a matrix, you need to take the row and make it a column. Take a row, make it a column. Your first row becomes your first column. Your second row becomes your second column. So I'm going to have 1, 1 here, minus 1, 2. Right? So the inverse of m is actually going to be 1 over 3 times 1, 1, negative 1, 2. That is an inverse. If you're going to write it precisely, I'm going to have 1 over 3, 1 over 3, negative 1 over 3, 2 over 3. So that is the inverse of m. So what I'm going to do, I'm just going to follow up the formula and prove it. So it's m1, m to the power minus 1 times a. Now in this case, a is p, so I'm going to have m to the power minus 1 times p times m must give you s. So it's 1 over 3, 1 over 3, negative 1 over 3, 2 over 3. I've written right correctly, yes. Now what is p? P, it is 2, 2, 1, 3. What is m? M, it's 2, negative 1. Lot, sorry. 2 minus 1, 1, 1. And this thing here must give you 1, 0, 0, 4. Then you have proven it. We have proven it. This is a proof. Now you can take a calculator, multiply that. So it's 1, 2. Take a calculator, multiply all these. You'll have 104. You can also find the inverse of a matrix using a calculator. But I was just showing you how you can do it using your hand. Right. So this is your diagonalization of a matrix. again, it also helps when you want to find p to the power 30, which means we are going to multiply matrix P 30 times. Right, P to the power 30. So it also helps you to find the powers of a matrix. But I'll just end the video here. The next one, we will look at how to solve the second order differential equations. Thank you. I'm just going to do one example, and I'll explain every detail that comes with that. Right, thank you.